Hey you guys, welcome back to another video. Today we're going to be discussing topic 1.4, which is called polynomial functions and rates of change. A polynomial function is any function representation equivalent to the analytical form p of x equals a sub n times x to the power of n plus a sub n minus 1 times x to the power of n minus 1 plus a sub n minus 2 times x to the power of n minus 2 plus plus a sub 2 times x squared plus a sub 1 times x plus a sub 0, where n is a positive integer, a sub I is a real number for each I from 1 to n, and a sub n is non-zero. Okay, so that might look really scary at first. You do not need to remember this formula. All this is trying to explain to you is that polynomial functions are going to have exponents that are positive numbers, and I mean that's basically it. So let me just give you an example. So let's say I say that n equals 10. Okay, just as an example, that means that this would be 10, right? If I look at the next exponent, it says n minus 1. Well, 10 minus 1 is 9. The next one is n minus 2, which would be 8. Okay, the next few would be, if I'm going down by 1 every time, 7, 6, 4, 3. The next one is 2. The next one would have to be 1, and the last one would have to be 0. So in actuality, when you have a variable that has no exponent, there's actually an imaginary 1 right there. And if you have a number with no variable, there's actually an imaginary x to the power of 0. Okay, so what this is saying is all of your polynomials should have exponents that are positive integers and that they're in decreasing order. Okay, so like for example, let's say 5, 4, 3, 2, 1, and then 0. So notice that the exponents are in decreasing order. Now you're not always going to have all of them. Like let's say this whole thing was missing, it would just be 5, 4, 2, 1, and then 0. So you're not always going to see all of them, but if you have some, just order them from greatest to least. The reason that all whole numbers or any number actually has an imaginary x to the power of 0 multiplied to it, and you actually have never seen it, is because any number to the power of 0 is always 1. So let's say if I say x is 5, well, 5 to the power of 0 is 1. If I say 1,000 to the power of 0, that's still going to be 1. So really, this is a sub 0 times 1, and anything times 1 is what you started with. So that's why you don't really see the x to the power of 0, but because today's lesson is all about finding exponents, it will be beneficial to understand that a constant number is technically being multiplied by an imaginary x to the power of 0. Okay, it's kind of the same concept as you don't really write 1x, you just write x because the 1 doesn't really do anything. It's kind of the same concept. Like you're not going to multiply x to the power of 0, which is just times 1, because again, it's not going to do anything. So when it says n is a positive integer, that means that your exponents need to be positive whole numbers. Okay, so whole numbers, positive, would be 0. I mean, 0 is not really a positive number, but 0 would be included, I guess. 0, 1, 2, 3, 4, 5, 6. You're not going to have negative 5, negative 7, negative 3, negative 1. You're not going to have negative exponents. So they should all be positive whole numbers. And then we have a few definitions here. So the leading term is going to be your term with the highest exponent. When they're talking about the degree, all they're really saying is what is the exponent. That's just a fancy word of saying exponent. And then when they're talking about the leading coefficient, we should know from Algebra 1 that the coefficient is the number in front of the variable. The variable is usually x. It's not always x, but most of the time it's going to be x. Okay, so if you're looking at this example when I gave it to you, remember I said 5, 4, 3, 2, 1, and then 0. So the leading term is a term with the highest exponent, so that would be this term right here. And that was just an example that n was 5. We're going to use the general one they wrote here. So for my leading term, I'm going to write a sub n times x to the power of n. Now your a and your x should be the same size. The only small ones are the n's that's below and above each respective letter. Okay, now we're looking at that leading term. The degree of that term is n because the exponent is n. And the leading coefficient is the number in front of the variable, which would be a sub n. Okay, let's do example 1. Find the leading coefficient and the degree of the following polynomial functions. So if you look at a, it says f of x equals 3x to the power of 4 plus 2x minus 7. Okay, so remember, if a variable does not have an exponent, there's an imaginary 1 there. And if a number does not have a variable at all, there's an imaginary x to the power of 0 there. So what you're going to do is analyze all of your exponents, and then you're going to circle the term that has the biggest exponent. In this one, it would be the term 3x to the power of 4. Okay, so that's my leading term. From that leading term, I see that my leading coefficient is 3, and the degree is 4 because the exponent is 4. Okay, let's do another example. For b, we have y equals 12x minus 7x cubed plus 11. There's an imaginary 1 there, and then the 11 has no variable, so there's an imaginary x to the power of 0. I'm going to look at the exponents between 1, 3, and 0. The exponent of 3 is the biggest, so this entire term is going to be the leading term. Notice that I took the negative with me. You're going to want to do that. The leading term will not always be the one in the very front. It might be somewhere in the middle. And if it is in the middle, you need to take the sign in front of that coefficient with you, because that's going to be important. Okay, so the leading term is negative 7x cubed. The leading coefficient is negative 7, and the degree is 3. For c, we just have the number 4. So remember, there's an imaginary x to the power of 0 there. And there's only one exponent, which is 0. So that's the leading term. It's the only term. So the leading coefficient is 4. And the degree is 0. Okay. For extrema, the extrema of a graph are the minimums and maximums of a function, and there are two types of extrema. You can have relative extrema, which are also called local extrema. A polynomial has a relative minimum or a relative maximum where it switches between decreasing and increasing, or at an endpoint if the polynomial has a restricted domain. When it says switches between decreasing and increasing, all that means is that your slope is changing from either going up to down or from down to up. Okay, so to figure out where your minimums and maximums are, you first need to figure out where your graph is changing directions. You read everything from left to right. So at the beginning, I see that I am going up, and then I switch to going down, and then I switch back to going up, and then I switch back to going down. So all of these times that I'm switching directions, there is a minimum or a maximum point there. So right here I changed, there, and right here. Okay, now it also said in parentheses or at an endpoint if there's a restricted domain. So all the way over here there is an endpoint, so that will also be considered a minimum or a maximum. The other side has an arrow, which is not an endpoint, so that will not be included as a maximum or a minimum. Okay, so we know that at the very top we have maximums, so this will be a maximum, and this one will also be a maximum. At the bottom we have the minimums. Okay, now all maximums and minimums are going to be considered local. Okay, so I'm gonna go and label all of these local minimum, local max, local minimum, and local max. They will all be considered local no matter what. Okay, And then remember, another word for that would be relative. So I can say relative minimum, relative max, relative minimum, relative max. It's the same exact meaning as local. And you will be expected to know that both are interchangeable. So make sure you know both words. We're all going to have a preference of one over the other, but don't get comfortable with only one word and then you forget what the other word means, okay? So relative and local mean the same thing, okay? Now at the bottom, they want you to label the x values of the local minimum. So the first local minimum was at x equals -4. I'm going to separate my second one with a comma, and I see my other local minimum was at x equals 0. Okay. For the local maximums, they occurred at -2 and +3. So I'm going to label those there. Okay. All right, the second type of extrema are called absolute extrema or global extrema. Of all the local maxima, the greatest is called the absolute maximum, and the least of all local minimums is called the absolute minimum. So these two graphs are actually the exact same. Now remember, all of them are already local. There's only going to be one or two special ones that are local and absolute. So to figure out what the absolute maximum is, you want to figure out what is the absolute highest point of the graph. I see this one here, and if I were to draw a point through here, you see how there's nothing else above here, it's completely blank. That means that this one would be considered my absolute maximum. Let's say you didn't know that and you thought it was this one. Always do a horizontal line through it, and if you see anything above your line, that means that that's not the absolute maximum. Okay, then you got to move up a little bit further. Okay, now earlier we had seen this arrow and we kind of skipped through it. Okay, anytime you see any type of arrow, I want you to circle that arrow and I want you to write no absolute minimum next to it. Okay, so if you have any arrows pointing down, there's no absolute minimum. If you have any arrows pointing up, there is no absolute maximum. Now, some of you guys might have seen this point and said, oh yeah, that's my absolute minimum because there's nothing below that. Now, that's what the graph wants you to think because they're gonna, be hoping that you're going too fast and not paying attention. But remember that arrow that I just circled? This arrow just means that I'm going down forever, never, never, never. Okay, and it's never going to stop. So in actuality, this one over here is not considered an absolute minimum because the graph is going to go down to infinity forever and ever. It's going to get lower and lower. Now, we can't say that infinity is the minimum because minimums have to have a numerical value, and we don't know what the value of infinity is. We don't know what the last number is. So that's why we say it goes to infinity. So again, if it goes up forever, no absolute maximum. If it goes down forever, no absolute minimum. Okay, the only way that you can have more than one absolute max or more than two absolute minimums is if they're at the exact same y value. So remember we said earlier, this was the absolute maximum. Let's say that this graph actually went up a little bit further like this and that they were both at y equals 2. That would be the only way you can have two absolute maximums. Or even if this one went up again and it was like that, then you can have three absolute maximums, but they have to all have the exact same y value for you to have more than one absolute maximum. And then the same concept for the minimum, they would all have to be at the exact same y value. Okay, now to write your absolute minimums and maximums, they're going to give you a blank and then it's going to say at x equals. In the first blank, you're going to insert your y value, so that's going to go there. Your absolute maximum occurred when y was equal to 2 at x equals 3. And then for the absolute minimum, since it went to infinity, there was none. Okay, let's go to the next page. We're going to do some more examples. So for example 2, you're going to start off the same way that we did the other one, which is labeling when you go up and when you go down. So when you start off on the left, I see that I'm going up until about there, and then my direction changes and I'm going down, which means that right in the middle, I have some kind of extrema. Specifically, it is a maximum. Now remember that all minimums and maximums are going to be considered local. But if you look at this graph, there's nothing else above this, so it's not only local, but it's also going to be absolute. okay? And then I see two arrows pointing down, which means that I'm going to write next to that, there is no absolute minimum. No absolute minimum, okay? So for relative minimum, there wasn't any, so I'm going to put not applicable. For relative maximum, it occurred when x was equal to 1. The absolute minimum, not applicable because it goes to infinity. And then the absolute maximum occurred when y was 3 and x was equal to 1. Okay, let's do another example. So again, start off by drawing when you're going up and down. So at the beginning, I go down, and then I switch to going up all the way to about here, and then I switch back to going down. Okay, so every time you switch, you're going to have a minimum or a maximum. So I switch there and I switch there. Remember that your endpoints are also included. And then every time you see an arrow, I want you to circle it and immediately write that there is no absolute minimum, just so that you don't forget and you don't make any mistakes. Okay, so over here I have a local max. Down here I have a local minimum, local max. Okay, now let's see if I have any absolutes. I think it might be this one. There's nothing else above this, so this one is local and absolute. Okay, and then we already said there was no absolute minimum. So the relative minimum occurred at x equals -2. We had two maximums, one at -4 and one at 3. There was no absolute minimum because it went down to infinity. And then the absolute maximum occurred when y was 2 and x was 3. Okay, let's do another one. So again, start by writing when it goes up or down. On this one, we start going down, and then we switch to going up, and it changes back down, and then finally it goes back up. So every time you change directions, go ahead and make a point there. You know that there's going to be an extrema, and if you have any endpoints, those are also going to be extremas. So both of these had endpoints on either side. Okay, so I know the ones at the bottom are going to be local minimums. If you're confused about what the endpoints are, just look at what it was before. You can't go from a minimum to a minimum. So that means that this one has to be a maximum. Okay, and they're all local. This one, local max, local min, and local max. They're all always local, and they should change direction. Again, you're not going to go max to max or min to min. It should be max, min, max, min, max. You're like alternating. Okay, so don't put two back to back. It should be max, min, max, min, max, min. Okay, let's see which of these is the highest. Oh, I have a very high point up here, so that means that this one has to be local and absolute. And then the one all the way at the bottom here will be my local and absolute minimum. Okay, so for relative minimums, I have x values at -3 and +3s. For the relative maximum, the x values are at -4, 0, and 5. For the absolute minimum, it occurred when y was equal to -3 at x equals -3, and the absolute maximum was at +4 when x was equal to +5. Okay, so some fun facts about polynomials. Between two real zeros of a polynomial, there must be at least one local maximum or a local minimum. And then just a reminder that another word for local would be relative. So either or, you need to remember both. And then in case you forgot from back in the day, a real zero is just an x-intercept. So all this is saying is that in between two x-intercepts, you're always going to have either a maximum or a minimum. So I'm going to show you that on this graph. So I have an x-intercept here and there, and in between that, we have a minimum. Okay? In between this x-intercept and that x-intercept, we have a maximum. In between this x-intercept and that x-intercept, we have a maximum. So that's all that's saying. So if there's two x-intercepts, that means there has to be either a local max or a local minimum in between. Okay. Now polynomials of even degrees must have either a global maximum or a global minimum. And then again, just as a refresher, the word degree means exponent. And another word for global is absolute. Okay. So an example of a polynomial that would have an even exponent would be like x squared, right? And we know that x squared is a parabola that looks like this. This one would have, let me write this down just as an example. Okay, so if you have a positive x squared, you're going to have a parabola that looks like this. So you would have an absolute minimum. And just another example, if you had negative x squared, you would have a downward facing parabola like this, and then you would have a global max or an absolute max. It's the same thing. Okay, so if you have an even exponent, so let's say exponent of 2, 4, 6, 8, anything like that, it'll either be an absolute maximum or an absolute minimum. And then depending on whether your coefficient is positive or negative will determine if it's a minimum or a maximum. So if you have a positive coefficient, it's an absolute minimum. And if you have a negative coefficient, then it's an absolute maximum. Okay, let's go to the next page. Now we're going to talk about points of inflection. A point of inflection occurs when a function changes from concave up to concave down or from concave down to concave up. So you're basically switching from a smiley face to a frowny face. At a point of inflection, the rate of change of a function changes from increasing to decreasing or from decreasing to increasing. Now, this is just another way of saying this. Okay, so I'm going to put that these mean same thing. They are two different ways of saying the exact same thing. Okay, so this is not to be confused with maximums and minimums. So maximums and minimums occur when your direction changes, right? So when your slope changes from increasing, when your when your line is going up, and then when your line changes to going down, that would be a maximum or minimum. For a graph, when your graph changes from a smiley face to a frowny face, that would be a point of inflection. So for these, you're not going to do your up down arrows. Instead, you're going to figure out where your smiley faces and frowny faces are. So at the beginning, I can see that I have a smiley face, and I'm gonna keep tracing that, and it's kind of actually about -1, because if you notice, after that it actually starts turning into a frowny face into about right there, at which point it becomes a smiley face again. Okay, so whenever your concavity changes, you can bubble. So we changed here and there, and what I want you to do is call that your point of inflection. You can just put POI. Okay, so for example 3, they wanted us to find any x values where g has a point of inflection. We already found that, so we'll say g of x, actually I'm going to say the graph of g of x. Let me move this over somewhere. Okay, the graph of g of x has 2 points of inflection at x equals, and then we have put them down at x equals -1 and where x equals +1. Okay. For each of the following intervals, determine if the rate of change of g is increasing or decreasing, and explain your reasoning for each answer. Okay. So when it says that the rate of change is increasing or decreasing, so when it says rate, remember when you have the word rate of change, I want you to write it in front of the other word. So you can say rate of change is increasing or rate of change is decreasing. Rate of change is increasing means smiley face, and rate of change decreasing means frowny face. Okay. Another key word is going to be this one that says intervals. So anytime they tell you, I'm about to give you an interval, that's not a coordinate point. They're actually going to be giving you x values to go look at. So for example, 3 to 4, it kind of looks like it could be a coordinate point. You're like, oh, that's my x value and my y value. No, because they said it was intervals. So that means they're telling you, go look from this x to that x. That's x sub 1 and x sub 2. So what you're going to do is go to the graph where x is 3 and 4. So that's from here to there. Now within that little sliver, they're asking you, do you see concave up or concave down? This was part of my smiley face, so I know that from 3 to 4, I'm concave up, so my rate of change has to be increasing. So I'm going to write on here that the rate of change of g of x is increasing because g of x is concave up. Now let's do the next interval, which is -4 to -3. So I'm going to look -4 to -3. And again, you see that we're part of that smiley face. So that entire, even though it looks like the graph is going down, which it is, it's still part of the smiley face, which is concave up. So the answer is going to be the same. The rate of change of g of x is increasing because g of x is concave up. The next interval is -1 to 1. I have -1 and 1 here, and you can see that that's part of the frowny face, which means it's concave down, which means the rate of change is decreasing. So we'll say the rate of change of g of x is decreasing because g of x is concave down. Last one, from 1 to 2, we got 1 to 2. You see that's part of the green smiley face. That means that that is also concave up, which means the rate of change is increasing. So we'll say the same thing, the rate of change of g of x is increasing because g of x is concave up. Okay? So that's pretty simple. You don't have to worry about whether your slope is positive or your slope is negative. It's not asking you, were you decreasing? It doesn't matter. If you were part of that smiley face, that's all that matters. They're not asking you about slope. They're asking you about concavity. Okay? Let's go to the next example. Example 4 says from 0 to 3, the number of cars in a parking lot at time t hours can be modeled by the function c of t equals -1.37 times t to the power of 5 plus 4.218 times t to the power of 4 minus 0.357 t squared plus 3. Based on this model, at what time t does the number of cars in the parking lot change from increasing to decreasing? Okay, so I know that I'm trying to figure out at what time t, okay? So that's supposed to be my answer. At what time? That's my question. And then it's asking me when it changes from increasing to decreasing. I know that that means that the slope is changing. So slope changes from going up to down or vice versa, okay? I know that it's slope because it didn't say the rate of change. Nowhere on here did it say the rate of change. Okay, so anytime it says rate of change is increasing or decreasing, then that's concavity. but because it said just increasing and decreasing, that's talking about your slope, whether it's going up or down. So what we're going to do is go to our calculator, and I'm going to add a graph, and I'm just going to type that in. Okay, so that was negative 1.37. Now the question says t, the variable is t, but you cannot put t and the n spire. So you're just going to manually change it to x. It's not going to change the problem, it's just a different letter for the variable. And then we got x to the power of 4 minus 0.357 t squared plus 3. And then you're going to press enter, and you're going to see something that looks like this. Now this is a real life problem with the independent variable being time and the dependent variable being the number of cars in the parking lot. So if you are given a real world scenario, you want to think logically about it. In a lot of real world scenarios, you're not going to have negative values. Like you can't have negative time, negative height, negative age, negative distance. In this example, we can't have negative hours, we can't have a negative number of cars. So for that reason, we're going to actually only going to focus on what is in quadrant 1. All the values that are negative are going to be irrelevant to this problem, again, because it's a real life problem. So I'm going to zoom out, and I'm going to focus only on what is in quadrant 1, which is this right here. Okay, it's actually about just that right there. Okay. No negative values. So what I'm going to do is I'm going to sketch this into my notes. And again, only drawing quadrant 1 because it's a real life problem. So for my x variable, we have time, and the y variable is the number of cars. So if you saw that, it started somewhere over here, and then it went up really fast, and then it decreased like this. Okay, so you can see for the most part I drew it about the same. So then the question was, when does the slope change from going up to down? Okay, so what I'm gonna do is label when I'm changing. So when I start, I go up, and then after that point I go down. Well, we just learned that point where you change from increasing to decreasing is called a maximum. Okay, so I'm actually looking for the maximum. Okay, so what I'm going to do is go back to my calculator, and I'm going to put menu, analyze maximum. You're going to get this dotted line. You're going to put it, you don't want to put it right on top right here. You want to put it a little bit to the left and then let it go. And the word maximum and the point should come up. And it's at 2.45, 31.9. So that means that the maximum, if you were to interpret it, that means that about 2.5 hours, the maximum number of cars in the parking lot is 32 cars. It might be that there's only 32 parking spots in the parking lot, so maybe that's why there's only 32 cars in there. Something like that might be the reason why, but that doesn't really matter. Okay, so what I'm gonna do is copy that maximum into my notes. So the maximum t value was at 2.45. I'm not going to worry about the number of cars because, again, the question was what time t. So I really only needed to know the t value. Okay, so now we'll write our answer. At time t equals 2.45 hours, there's a maximum number of cars in the lot, comma, and the number of cars in the lot changes from increasing to decreasing. Okay, now if you think about it, this problem is not difficult. Okay, all you need to do is graph it and all that. The real meat of the problem is making sure you understand what they're asking you. You need to know that increasing and decreasing means slope, because some people might have said, oh, that's talking about the point of inflection, and the point of inflection is where it changes from smiley face to frowny face, so that would have been somewhere right here, right? So you need to understand the difference between the graph is changing from increasing to decreasing, and the rate of change is increasing to decreasing. So that's what they're actually testing you on. Do you know the difference between like the slope going up or down, and do you know the difference between concavity changing from a smiley face to a frowning face? So that's what example 4 was, making sure that you understood. Okay, then the actual graphing part and finding the maximum, that part is not difficult at all. Okay, last example, it's 2 parts. We're going to be sketching a polynomial function on each axis provided that has the following properties and the domain from negative infinity to positive infinity. Letter A says f of x has 2 points of inflection, 1 absolute maximum, and no absolute minimum. Okay, I actually forgot to tell you something important. Sorry, my bad. So we're going to go back up to this page here, and I want you to write off to the side that the number of points of inflection is 1 less than the number of smiley faces and frowny faces. Okay, so here we had 1, 2, 3 smiley faces and frowny faces, so 1 less than that would be 2 points of inflection. So if you have 2 points of inflection, you'll have 3 different changes and so on and so forth. Like, let's say this part of the graph wasn't there and we only had a smiley face and a frowny face, that's 2 changes, so there's only 1 point of inflection. Okay, so that's going to help us try to sketch these, because if it says f of x has 2 points of inflection, that means there should be 3 different smiley faces and frowny faces. 1 absolute maximum, we just need to make sure that we put one of the points up really high up. And when it says no absolute minimum, remember that at the end we should have an arrow that's pointing down, and that would indicate that there's no absolute minimum. Okay, so I'm going to sketch something. I'm going to start with making sure I have my absolute maximum. So I'm going to start by going up really high, just so I make sure that I have that maximum. Okay, now I know that I need to change directions quite a few times. So right now I have a concave up. So I'm going to go and switch to a concave, I had a concave down. I want to switch to include a concave up. Now I only have 2. So I still need 3, which means I'm going to have to go back down. But I don't want to go too far up, because then I won't have that absolute maximum. So I'm going to just put it about right there. Okay, now at the ends I'm putting arrows, because these arrows again are going to indicate that there is no absolute minimum. Okay, and then up here we have our absolute maximum that we needed. And then if you notice, for the direction changes, we have this part, which is concave down, and then it switches to about concave up, and then we have concave down again. Now my graph is like really ugly. You can make it a little bit more smooth. So these are all sketches, so everyone's just gonna look a little bit different. For example, you could have started off a little bit shorter here and then made this one your tall side, and that would still satisfy all the requirements. So everyone's graph might look a little bit different. We all have different interpretations, but just make sure that you hit all of the points that they're asking you to include in your sketch. Okay, for letter B, g of x has 1 local maximum, 2 global minimums. So remember, in order to have 2 global maximums or minimums, they need to be at the same y value. Otherwise, you can only have 1. Okay, so we need to have 2 minimums that are at the same y value, and then we need 2 points of inflection, which, remember, that means that we're going to have 3 smiley faces and frowny faces. Okay, so if I were to start the same way, which is like this, I could have a local maximum, but I'm not going to have two global minimums at the same spot. So it gets a little bit difficult. So it's actually easier if you start upside down. So if, for example, I start down and I'm going to include my minimums, let's say I want to pick this y value right here, and then I'm going to have, I need a local maximum. And then if I include my other global minimum, it should be at the same exact y value. Okay. So there we have that. So let's make sure we included everything. So we have two absolute minimums, which are both at the same exact y value. I have a smiley face till about there, and then a frowny face, and then I have another smiley face. So I have three different changes in direction, and then I do have a local maximum right here. Okay, so again, everybody's graph is going to look a little bit different. So you have some practice problems that look like this on your homework. Just, make sure that you follow everything. It might take you a few different attempts to get the correct thing. So, you might start like this way and then realize, oh wait, that's not right. I'm not getting what I need, and then you got to change directions and see if maybe if you start backwards, if that'll fix the problem. So just don't give up and try your best. And if you have any comments or concerns, let me know down below. See you guys in the next video. Bye.